Alright, sorry I can't go to Recitation this Friday. I'll try to record a quick video. Hopefully this won't take too long. Just to go over some of the recitation stuff, so you guys feel like you got something and not just left in the dark. I haven't actually looked through any of this yet, so if you want to watch it on 2x speed, it might take me a second to remember things. And I'm not going to give you guys the answers directly. I'm going to make sure you're on the right way, though. All right, number one, the key mechanism of an E2 reaction is a strong base. For secondary alkyl halides, a one-step E2 elimination mechanism is generally competitive with the SN2 mechanism. Use curved arrows to draw the E2 mechanism for each possible alkene product and predict which is the major alkene product. All right, the important thing to remember here is what is the first step in an alkene or an elimination? The base is going to attack the beta hydrogen. This is the alpha carbon, this is the beta carbon, and then the beta hydrogens are the hydrogens that are attached to the beta carbon, and you can see that this is also beta, so there's going to be two hydrogens off those, and those are all beta hydrogens. So you know that the mechanism, I'll just give you guys the start, is going to start with an acid-base reaction. The base comes and attacks that, or it also could come and attack the other beta hydrogen. That should be enough information for that. Predicting the major product is dependent on what the base is. If you remember, the small, not bulky bases, but still strong, will have an E2 mechanism that will produce the most stable, or the Markovnikov product. And then the larger bases will produce the kinetic product, which is attacking the beta hydrogen that is least sterically hindered. And that kind of makes sense because it's a big base. It can't get in to attack a hydrogen that is sterically hindered. I'll give you another big hint. That is a small base. It's not a terp butoxide or anything like that. All right, B, based on the E2 transition state, provide an approximate E2 rate equation. If you remember, E1 happens in 2 steps, and one of those 2 steps is the rate limiting. E2 happens all in 1 step, which means the only step is the rate limiting step. And that also means that everything, all of the reactants have to be, where's my lady? All the reactants have to be included in the rate equation. It's a big hint. All right, SN1 reaction below for 2 is called solvolysis reaction, since the nucleophile is the same as the solvent. Analyze the alkyl bromide and nucleophile and explain why an SM1 mechanism is more reasonable, lower in energy than an SM2 mechanism. Okay, if you guys remember, I sent you this chart. Reasons that an SN1 would be more likely than an SN2. Primarily, it has to do with the structure of the carbon or the organic group that you're reacting with. Tertiary is always SN1. Primary, always SN2. Primary never is going to be SN2 or SN1, and tertiary is never going to be SN2. So, looking at this structure, I'm sure you guys can look at this and figure that out, why it would be SN1 and not SN2. Explain why the carbocation intermediate is reasonable to propose. I don't know. I think that this is just asking, like, why is the specific carbocation that forms in this reaction relatively stable compared to other potential carbocations? Like, yeah, that was bad. This structure might not be as stable, or even this structure won't be as stable. So explain why that carbocation, the intermediate, is more stable. Draw the SM1 reaction coordinate energy diagram. This was last test type stuff. Wait a second. Am I on the right recitation sheet? Oh yeah, I am. That's weird. Yeah, so you guys know how to do that. Typically, in parallel to the SN1, based on the SN1 mechanism, predict the products. That's also from the last test. Just remember to include both products. SM1 reactions yields 2 products if there's stereochemistry. Typically, in parallel to the SM1 reaction mechanism and substitution products, alkene products with pi bonds are also observed. From the carbocation intermediate, draw the reaction mechanism leading to possible alkene products. I wonder if I can. Let me think about this real quick. So this is just referring, specifically, it's referring through E1. Because during every SM1 reaction, you'll also have E1 side reactions, and it's really not that specific. You can control it a little bit with temperature, but yeah, every SM1 reaction will yield some side products. So from the carbocation that forms, let me pause real quick. You guys can fast forward through this. Okay, yep. You know that the first step of a E1 reaction and SM1 reaction will be the same. Bromine will leave. And then with this specific reaction, remember to always look at the beta carbon and then from that carbocation, look at the beta carbons and then the hydrogens that are attached to that for the second part of the reaction, which is the acid-base reaction. I'm not going to give it too much away, hopefully. And then that will form multiple alkene products because there's 3 different beta carbons. So that's just the things to be aware of. That's what I would look for. Always start by looking at the beta carbons. That way you can know how many products are possible. F. Explain why starting 2-bromo 1,3-dimethyl cyclohexane instead of alkyl halide shown below will lead to the same substitution and alkene products. All right, well, I think the only way to do that is to draw it out. I would start by drawing this out, 2-bromo 1,3-dimethyl cyclohexane. So there we go. So that's the starting product. And then carbon will leave. Leaving that carbocation. And this carbocation would be like that. So as you can see, they're very similar. The methyls are in the same place. And then if you look at the hydrogens that are beta, you can form at least one product that's the same by attacking the hydrogens that are across this bond right here. That's enough information. All right. Elimination reactions replace stronger sigma bonds with slightly weaker pi bonds. In other words, elimination reactions are slightly exothermic. Often, endothermic reactions have poor, but elimination reactions are often favorable. Often endothermic reactions have poor. What does that mean? Let me see if This is the correct question. Oh, poor. This is missing a word. Have poor yields. But elimination reactions are often favorable. Why? What else is going on that can help push the equilibrium towards products and increase yield? Okay, I think the best thing to think about with this, what is, like, to start off, the thing that's going to make a reaction spontaneous and favorable is if Gibbs free energy is negative. If you guys remember that equation from those other chemistries. This is entropy. This is enthalpy. And with this equation, you can answer both parts of this equation, or both parts of this question. Question 4, predict the elimination mechanism by which the following reactions proceed and draw the structures of the expected major and minor products. If there are more than one product, identify the major and the minor products. It will help you your product prediction to draw the mechanism for each reaction. All right, so to start off with the first one, what I always like to do is first off, I look at this. What type of carbon is this attached to? Is a secondary carbon. With elimination reactions, that doesn't make as big of a difference because tertiary is always going to be the fastest for E2, E1 and E2. So that doesn't matter quite as much. So the next thing, look at the solvent. That is the next big step. And if you look on here, look at the solvent. If it is, or solvent and the nucleophile, sorry. So in this case, the solvent is the nucleophile. In this case, different solvent, different nucleophile. In this case, the solvent is the nucleophile. So if you look at the nucleophile, E2 is favored by strong bases. It could be a strong big base, like tert-butoxide, or a small little base. And then elimination reactions favor, or the E1 are favored by weak bases that are often also just the solvent, like these. So I think that's enough information right here. I think this one is a little bit tricky because this has a strong base, but then it has a protic solvent. So it has the strong base right here, but it has a protic solvent. The strong base should favor E2, but the protic solvent should favor E1 because the protic solvent, as you know, acid-base stuff would happen right here. Kind of kill your strong base. So that's kind of a tricky question. But honestly, like, I'm just going to let you guys know that it seems to be targeting the E2 reaction. And maybe the solvent, like this would just be a poor choice of solvent if this was a chemist doing this reaction. It should be a polar aprotic solvent, or no, wait. Yes, a polar aprotic solvent. So that's just a poor choice of solvent. But I've probably said too much already, so you guys can figure it out from there. A common feature of SM1 and E1 reactions is that they form carbocation intermediates. Though all carbocations are highly unstable, we know that because of hyperconjugation, tertiary carbocations are more stable than secondary carbocations, and primary carbocations are so unstable they never form. Whenever a secondary carbocation forms an intermediate, hydride and alkyl shifts can occur in order to turn it onto a tertiary carbocation. Keeping this in mind, use curved arrows to show the mechanism of the following reactions. Cool. How far are we? Oof. We'll blast through the rest of this stuff, hopefully. All right, so with this, the first step in an E1 or SM1 reaction is the leaving group leaves. And in this one, it's the dehydration of alcohol, acid catalyzed. You guys talked a lot about that. You should know that first part. But it's going to leave to this with a secondary carbocation. And that can lead to both hydride shifts and methyl shifts. Actually, not really a methyl shift, but it can definitely lead to 2 different hydride shifts. So just think about, try to move that plus around by doing a hydride shift in all the possible ways you guys can to form these products, and then that's how I would start. That shouldn't be too tough. Draw the mechanism for the following reactions and indicate the product stereochemistry. Note the textbook would use pyridine instead of triethylamine. They're both weak nitrogen bases and do the job interchangeably. So the big thing to remember, socyl and pocyl. Socyl, because it has the S, does substitution. Pocyl, I don't know if there's a good way to remember this other than it's not socyl. You could think of maybe the P, it pulls everything off, so it does the elimination. And this one is just straight up asking for the mechanism. That's something that you guys can go and find in her notes. Let me see if she's posted those. If she hasn't, I'll run through a little practice mechanism real quick. Which chapter is this? Good news. She has the notes for that. So just look at if you have no idea where to start, she has the mechanism very clearly written out in her notes. So just go to her notes to find how to do that. And like she said, ethyl or triethylamine just looks like this. How do I think about that? So that's triethylamine. It just acts as a base. This is the nucleophile. The lone pair is the HOMO. All right. Compare the alkenes formed. Actually, going back to this one, as a side note, on the test or on any assignment, if you're pretty confused about something or confused about what the products are going to look like, a lot of the times there's just going to be something like this, and in the test all you need to do is draw the supposed product, whatever it is. I'm not gonna draw the whole thing out. If you have trouble just memorizing how these reactants will affect a specific solvent or a specific reactant, then just draw out the full mechanism every time, even if it doesn't say you have to. Just so there's you take out all of the unsurety, all the guesswork, and then you can have the logical foundation for how the product is formed. That's what I would recommend for all the test questions. And yeah, so these ones also are clearly outlined in her notes. I would just go to her notes, look at those mechanisms, and I don't think there is much more to that than just drawing out the mechanism exactly as she has in the notes. I'm not going to give you guys the exact answer. I believe she also talked about this. And I think this has to do with stereochemistry or regioselectivity. This does. So when you're doing that, just think about that, I guess. Unlike the electrophiles we've dealt with so far, epoxides have two possible sites of attack by a nucleophile. A, predict the products for the following reactions, including drawing the reaction mechanism. B, use transition states to explain why acidic conditions favor substitution at the more substituted carbon, while basic conditions favor substitution at the least substituted carbon. Perfect. Okay, I don't know if she talked about the second part. I think I'm just gonna draw some random fake epoxide that doesn't look too similar to the question to give an example of why. Oh, that's way too similar. Yeah, whatever. It was gonna be pretty similar either way. There's only so many epoxides you can draw. Cool. Ours will look like that. So I'm just going to give an example and show you guys like the logic for why, at least my logic for why acid catalyzed epoxide ring opening will favor the more substituted and the base will favor the less substituted. So always in the presence of a strong acid, almost every time, if there's an oxygen like this, it's gonna deprotonate. Whatever. Something like that. And then it'll be a positively charged epoxide. And looking specifically at this structure, if you want to think about the sterics and how that positive charge is going to affect the bond between this carbon and this carbon, I like to think that the positive charge will push it farther away from where there are more sterics. If that makes sense. So like this is kind of like what that transition state might look like with an acid catalyzed epoxide opening. And then obviously you can see that this bond is now way weaker than that bond. It's way more prone to breaking. And then that's when your nucleophile will come in and attack right there. When the epoxide opens under basic conditions, these are about the same distance. This bond is about the same strength as that bond. So obviously the base would just come into the less sterically hindered site. And I hope that makes a little bit more sense about why that happens. Predict the single product of the E1 reaction that occurs under the following conditions. Note that the first step of this mechanism will be protonation of the hydroxy group to turn it into a good leaving group. Why is there only one E1 product? That is a great question. Let me look at this for a second. Think about it. Oh, okay, I get it. So a lot of you might be thinking about how the hydrogens have to be antiperiplanar from each other, or for instance, in a typical E1 reaction, actually E2 reaction. If you have a strong base, do that. It's just simple. If you're gonna have a strong base, it's gonna attack this, and that's gonna pop down there, and that's gonna pop down there. All of this reaction site have to be on the same plane. And that's called, or the term we use is that the chlorine is anti-periplanar from the hydrogen. So with E2 reactions, it has to be like that. This is not talking about that concept. So I'll give you that hint. If you think about one of the other questions that talk about secondary carbocations in an E1 reaction and what can often happen with the secondary carbocations, that would be very helpful. So maybe go back to a different problem, the other problem that talked about that. A bit more practice, write in the products or reagents for the following reactions. Okay, this is where I was talking about it. If you guys I think it's going to take a while just to intuitively know how Socyl and pyridine are going to affect the stereochemistry of this carbon, how the substitution is going to happen, and it's going to be hard initially to know everything behind that well enough just to be able to oh, I know the product right off the bat. So for a while, just draw the mechanisms, and it'll be really helpful in learning and just getting down the conceptual side rather than just memorizing it. A lot of people try to memorize their way through OChem, and you can get by, it just will take a lot more work. So yeah, that would be my recommendation for all of those problems. I don't think there's any terribly difficult ones. This one will be tough because you have to find the reagent, these two. But if you go back to the class notes, every single one of these have been talked about in depth. So I don't think I'm going to help you guys too much with that one. I have confidence that you guys can get that. Yeah, it's best if you work it out on your own anyways. All right. Well, I think that is everything. So good luck on the recitation sheet. Sorry again. If you can, go to Josh's lecture. He got a bigger room for it, so you guys are all welcome to go if possible. I understand a lot of you have class, so that is totally fine if you can't. But good luck. I'll see you on Monday.